It's a weird sound. You got this recording. I'll delete that. Safa, what's kicking?
I'm chilling. What about you?
Chilling, man. What's it look like? This is not even a reclining chair. I have to recline my body. I like the chairs like this, and the body's gonna go out diagonal to get the recline. That's how much I'm chilling. It's actively chilling.
Yo, same. I feel you.
Looks like it's just me and you right now, man.
Yo, the Tuesday crew. Let me know.
Tuesday crew, yeah. Maybe we'll give it a couple minutes, see if anyone shows up.
Got you.
You watching that World Series at all, Safa?
No. I don't really watch baseball that much, or like ever.
Just a basketball guy? Oh wait, NFL?
Yeah.
Yeah, we don't overlap. We don't overlap anywhere, stuff. Yeah, I don't know. See, the Tampa Bay has a shot. They're in the World Series right now. The series is 3-2, Dodgers beating Tampa Bay. But Tampa Bay has a shot to win. Tampa Bay Rays have a shot to win the World Series. Tom Brady's and the Buccaneers got a shot to win the Super Bowl. And then the Tampa Bay, their hockey team, I think, won the Stanley Cup this year.
Yeah, I think they did actually. That's a good year for Tampa Bay. Dang.
Point is, Tampa Bay could take it all this year. That'd be pretty crazy.
Yeah, that'd be insane, especially
Miami
after
almost won the NBA finals. So that would have been a full Florida sweep.
Ooh, that definitely would have been like a legendary year for Florida.
What's that say about America if we have a full Florida sweep? That's just proof that America's a spot. Herman Toro, what's going on?
Know it.
Me and Safa talking Tampa Bay. The Tampa Bay sports teams have almost won every single. Have a chance of winning every single sport they're in, except for probably like women's arena football or whatever, like minor league teams they have. We're not talking about that. We're talking about the big four: baseball, football, basketball, hockey. Oh, Tampa Bay has a basketball team, right, Safa?
Tampa Bay, like for the NBA?
Yeah.
I think it's just the Miami Heat.
Florida has the Miami Heat, the Orlando Magic.
Oh yeah, I forgot about the Magic, but that's
No
because they're
Jacksonville
trash.
team, right?
Nah, just for the NFL.
I'm so confused by Florida, like how big it is. Like they're just like they have Jacksonville, Tallahassee, Miami, Orlando, Tampa Bay. Like no wonder they're a swing state every year, or, I guess. But yes. Anyone have anything to add about Florida? Does anyone understand Florida?
Nope.
I went
no
to
idea.
Pensacola once.
On a research trip, I assume, to try to understand Florida. It's like the people that go in the jungle to study the monkeys.
Right, yeah. Floridians are a whole new breed of individuals.
Yeah, the Florida man. But anyway, I don't think we're gonna make any progress there. But a place we can make progress is discrete math. Who wants to get started?
I'm ready.
I do, and my vote counts for 74 votes because there's only 72 people in the class, so I automatically win. Let's get the screen shared. Safa's ready too. It's good to know. Thanks, Safa, for your input. So, look at this camera's all set up. Like I feel like we have to remember where this class started. Like every class, I'm like, oh, the camera's upside down. Let me set it up, see what's going on. Now it's like pretty perfect. Let's appreciate where we're at. The point is, we're still talking about sequences, and today a little bit of series. So let's get into it, which you might have went over in calculus, but you should have gone over in calculus if you had any calculus teacher worth their salt. We're gonna do it again because it's useful to us. So we're talking about section 5.1/5.6 sequences. It's series. All right, so remember that sequences we're going to do this every class, are things that look like this. And actually, we're just going to look at infinite sequences from now on, because that's really what we're concerned about in math. I mean, finite sequences are a thing, but in math, we like the ones that keep going. So infinite sequences always have the form am plus 1, am plus 2, dot, 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 meaning so forth, on and on like that. Meaning they are ordered, indexed lists of numbers that never end. That's exactly what an infinite sequence is. It looks just like this. Now, this way to write it, I don't even think there's a name for it. Let's call it standard form / written out form, or / written form, because it's kind of like writing it out manually. There's that. But there's also, there's also the explicit form. This is a very nice way to write out sequences that goes like this. Another way to write this same sequence out would be to write AI equals f of I for all I greater than or equal to m. The thing to note being f is a function dependent only on I, where I is the index. So the way we write something in explicit form is we just write out, we just write what each term is in terms of with some function dependent on the index. So an example of that would be if we had the sequence AI, and what I should say is that I want to be very clear here that this explicit form, very clear here, I should actually pronounce it very clear here, this explicit form is equivalent, actually I want this in blue. The explicit form and the standard forms to written out form are, okay, if they represent the same sequence, are equivalent ways to represent the same sequence. I don't want to give the impression that, oh, this is the actual sequence and like this is just kind of like a shorthand or something like that, or this is the actual sequence and this is a longhand or a shorthand. No, there are two ways of writing the exact same thing. We'll see that right now. So for example, we've done things like this before. Let's have the sequence AI equal to, and actually, yeah, AI equal to I squared plus I for all I greater than or equal to 1. And by the way, I'll just tell you, we'll call this the explicit formula. And we'll call this the range. Because this is the formula that tells you what each term is, and this is the range of values we're considering. So here our explicit formula that tells us what the ith term is in terms of the index I is this I squared plus I. This is the explicit formula here. And the range is for all I greater than or equal to 1. So we're starting at 1. And now an equivalent way to write this is just let's plug it in and figure out like what's the standard form of this. So we start at A1, which equals, because I is greater than or equal to 1, which equals, plug that in, we get 1 squared plus 1, which equals 2. Next we go to A2, which we plug the index 2 in, we get 2 squared plus 2, which equals 4 plus 2, which is 6. Or we could have A3, which plug the index 3 in, we get 3 squared plus 3, 9 plus 3 equals 12. On and on like that. Now, we've done this before. This is just how you go from explicit to standard form, right? You just kind of plug it in. The point is, the big point I want to get across is that these two things, these two representations here, are two equivalent ways to represent the same underlying concept. Oh, now we're getting philosophical. I almost said philosophical. The point being, let's look at it this way. Here. I think everything makes more sense if you look at it in terms of food. So look at chicken versus pollo. Which one is the delicious, flightless, domesticated bird? What do you guys think?
I think pollo is just chicken in Spanish. Well, I took Latin in high school, so like this is just a guess.
Wait, is there a Latin word for chicken?
Yo, that was too long ago. I can't tell you.
Did the Romans have chickens? Did they have cows? What did the Romans eat?
They definitely had cows. I remember memorizing the Latin word for ox. I can't tell you what it is right now though.
But it's not the same thing as a cow.
Not really.
I have no idea what people ate back in the day. I feel like I have no idea what the Romans ate, but I feel like the medieval people were definitely eating chicken and cows. So I don't know when that happened. Anyway, I want to talk about this. Also, let's talk about the fact that they found some chicken bones in the west coast of South America that look like Polynesian chickens. So I guess like the Polynesian chickens of the ancient Polynesians and the Indonesians, that area, what they had, are not the same chickens that like the Europeans had. And they found some chicken bones in South America that look like they're Polynesian chicken bones. And they dated them, and it was before 1492, which of course when the Columbus sailed the ocean blue. Meaning that possibly the Polynesians found South America. Who knows? The point is, Jordan Horman, Soph, what do you guys think? Which one of these is the delicious, flightless, domesticated bird?
Neither.
I
Well,
say neither,
both.
Thor.
Sorry, both.
Both?
Yeah.
Okay, so Safa says
Pollo is Italian for chicken, yeah.
So Spanish for chicken. Yeah, they're both the same
Something
thing.
like that.
so. Toru votes they're both a delicious flightless bird. Safa votes. All I know about Safa is they took Latin. Herman, what's
Both
your
also.
What's up? What?
was your vote also both?
What was the question?
Yeah, both.
Okay. Here's the thing. And I feel like I'm gonna get a bunch of moans about this, but it's important. The answer is neither. they're both words. Neither of these are the delicious flightless bird. Like if you were hungry and I placed a solid CHICKEN on your plate, that wouldn't help you at all, right? Neither. They're both words representing the same concept. That's right, chickens are concepts. It's just deeper than I go in this class. But it's actually a lot like, I don't know how cultured you guys are, but if anyone's seen, where do I want to go? Oh, now you see my research I've been doing. If anyone's seen this painting right here. Has anyone seen this? It's a cool little painting and it says, I don't know, friend, Ceci n'est pas un pipe. She's in the pipe. Which means this is not a pipe in French. The point the guy was trying to get across is that this is not a pipe, it's a painting of a pipe, right? And we often get those things confused, right? We often like see a picture of an apple and go, that's an apple, but it's not really an apple, it's a picture of an apple, right? And we have the same thing happening here with the chicken case, right? These are not chickens, or these aren't the delicious domesticated flightless bird. These are words for them. But they both represent the same concept. And that's the same thing happening up here. It's all around a way to get back to this. The same thing happening here. This sequence that I'm trying to get across here, right, could be represented like this or represented like this, where really maybe you want to write it as 2, 6, 12, ... so forth on like that. They both represent the same sequence, but neither of them are the sequence. That's the weird thing. The sequence is kind of this conceptual thing that we're trying to write down here, right? But these are both representations, and so is everything in math. For example, this is not 3, right? It's the representation that we give to the concept of 3. And I would love to get into we're going to get into what we're going to get into what 3 means by the end of this class, or not this class, the end of this semester. I'm very excited about it. The point is, does that make sense?
Yeah, it's kind of like saying that musical notation isn't actually music itself. Like
Exactly, right? Yeah, exactly. Like you see music written out with the little cool like quarter notes and all that kind of stuff, and that's not actually music. Like, it's not going to move you, whatever, maybe, you know what I mean? It's not going to get you hyped for a football game, right? Like, I don't know what you guys listen to music for. But the point is, yeah, it's representation of music. Kind of the difference there, though, Herman, is that I guess if someone actually played music for you out loud, you go, okay, now that's music, right? Math is a little slipperier in the sense that, I mean, where is the sequence? I said that these are both equally valid representations of the sequence. The sequence is kind of like the 3 thing. Like, where is 3? What would you look at and go, no, that's 3?
Well, would it be like a mental representation in your head? Like once you learn how to read mathematics, you could actually see the beauty inside your own mind, right?
Yeah.
Like that.
Yeah. I mean, I guess mathematical things really represent, the things you write down represents mathematical concepts that really only exist in our minds. That's a very weird thing, right? Like no one's ever observed 3. We can observe 3 things. Like these are 3 fingers. You look at, these are 3 markers right here. But, you know, but there's the abstract concept of 3 is impossible to be observed. It exists in our mind as a generalization. But we have different representations for it. And these are both different representations for the sequence. Anyway, yeah. The point is, the big point is, I don't want you guys to think that, oh, like this is a sequence and this is just kind of a weird way we describe the sequence. No, these are both equally valid ways to write the sequence. These are both equally valid ways to define a sequence. It's both defining this mental concept. By mental, I mean of the mind and also like freaking mental, man. Cool. That got deep for a second. I didn't want to erase that. Oh well. But anyway, so yeah, that's just a little tangent there about sequences. Now let's look at something we talked about last time, alternating sequences. Let's just do another example because we only did one last time. And so an alternating sequence, remember, it's a sequence that goes back and forth, negative, positive, negative, positive, negative, positive, or positive, negative, positive, negative, positive, negative. So an alternating sequence, we could have an example. And our example will be -1, 1/2, -1/3, 1/4, -1/5, 1/6, so forth and so on, like that. So see what's alternating because negative, positive, negative, positive, negative, positive. Just a particular type of sequence that has some nice properties. The weird thing is we're not even really going to get into the properties. I just want you guys to know how to deal with these things. So not deal with. Deal with sounds like live with. It sounds like you manage. I don't want you to thrive with these. So how can we write this as an explicit form? That's the big question. The explicit form for an infinite sequence like this is always going to have, well, you can use I or K or J or N. It doesn't matter what variable you use. The point is going to be some index variable. AK equals something for all K greater than or equal to something. So this defines your range. This defines your explicit formula. And so for alternating sequences, we kind of said that a good idea to figure out the explicit formula is to start here. Start by finding, wow, what an I. We're finding explicit formula for absolute value of sequence. Which in this case is, by absolute value sequence, I just mean the sequence without any negatives or positive, or without any negatives. Take all the negatives away. So we have 1, 1/2, 1/3, 1/4, 1/5, 1/6. And then here, I'm going to call this AK. So what's the explicit formula here?
I think Safa's mic's broken again. But he
Oh,
said
Safa's your
1
mic
over
broken?
I.
What'd you say, Herman?
He said 1 over I think.
Oh, thanks for the translation. Thank you, Safa. Exactly. 1 over I. Well, actually, since we're using the index variable K here, just to switch it up, it's 1 over K. Totally right idea. And then where's our range start for all K greater than or equal to what?
Zero. Oh no, 1. Greater than or equal to 1.
Exactly. Greater than or equal to 1.
Yeah.
If we started at 0, then our first term would be 1 over 0, which is no good. And we don't. It starts with 1, not no good. So yeah. So yeah. So this is kind of the explicit form for the absolute value of the sequence. Now the idea is to modify this to get to where we want. And the way you modify it is you either multiply by a -1 to the K or -1 to the K plus 1. Yeah, Herman's Safa's interpreter. Yeah. So so the way you do that is then you look at AK equal -1 to the K times 1 over K, or AK equal negative 1 to the k plus 1 over k. The difference between these two are that they'll be negative and positive in the opposite places. So it always depends on, does your sequence start negative or start positive, and what's your starting index. So if we try this one first, right, we get what? We get that A1 equals negative 1 to the 1 times 1 over 1, which is negative 1 times 1, negative 1. A2 equals negative 1 index squared, 1 over 2, which equals negative 1 squared is 1 half. A3 is negative 1 cubed, 1 over 3, which is negative 1 cubed is negative, so this is negative 1/3. It goes on and on like that. Versus this sequence, which would have A1 be negative 1 to the 1 plus 1, or negative 1, yeah, to the 1 plus 1, 1 over 1. Negative 1 to the 1 plus 1 is negative 1 squared, which is just 1 times 1, so it's 1. A2 would be negative 1 to the 1 plus 2, 1 over 2. Negative 1 to the 1 plus 2 is negative 1 to the 3. Negative 1 to an odd power is negative 1. This is negative 1/2. A3 is negative 1 to the 3. Actually, it's 2 plus 1, not 1 plus 2. It doesn't matter though. 3 plus 1 times 1 over 3. That's going to be negative 1 to the 4. Negative 1 to an even power is positive 1. So this is 1/3. Like that. So which one do we want to correctly reproduce this sequence? Pink or orange?
Safa said pink.
Yeah, pink, exactly. Thank you. I wonder why I can't hear him at all. That's interesting.
I have headphones in, so I think there's a bit of a, I can hear.
Oh, better, nice. So yeah, yeah, pink, totally pink, right? And pink is the one where you negative 1 to the k, negative 1 to the k plus 1. The point is, once you find the explicit formula for the absolute value of the sequence, you can just kind of guess and check here to figure out if it's negative 1 to the k or negative 1 to the k plus 1. Here's negative 1 to the k. And so we get AK is going to be negative 1 to the k times 1 over k for all k greater than or equal to 1. And again, these are two equally valid ways to represent the same sequence that we kind of have in our heads. The same abstract sequence that exists in the mathematical world. Interesting. Any questions? Good, because I have a question for you. And that is, how can we prove, well, actually, I guess, let's not even talk about, but let's just think if it's true or false. Can every sequence be written in explicit form? Every sequence can definitely be written in standard form, because standard form is kind of a direct way to write an ordered indexed list of numbers. But, well, it's kind of weird because you can't write all infinity of them. You can only write the first few with a ... So, but either way, the point is you can start to write every sequence in standard form. The question is, can every sequence be written in explicit form?
I'm gonna say no.
I say no, Herman.
I don't know if that's right or not. I'm just assuming because there are sequences, or at least there's like sequences that don't really repeat themselves in a consistent pattern, that you could write it in explicit form to always have it repeat.
Oh, that's an interesting idea. Yeah. For example, if you had the digits of pi, right? If you looked at, if you define your sequence to be the digits of pi, 3.14, 1, 5, 9, 2, 6, something. You define your sequence to be 3, 1, 4, 1, 5, 9, 2, 6, ... I mean, like, this is a valid sequence. It's a well-defined sequence. Like we know what comes next. It's just whatever the next digit of pi is, which we can calculate. Or I can't, but people can. But like Herman said, it doesn't really repeat. There's not a nice formula for it. There's not a nice explicit formula for it. You're totally right. An even easier one to see? Let's look at this guy right here. One, 2, 3, 5, 8, 13, 21, 34, on and on and on. Do you know what this guy is?
Fibonacci sequence?
Fibonacci sequence. Talked about this like two classes ago. Exactly. This right here is the Fibonacci sequence. And here's the question. Can we write it in explicit form? Well, what's the pattern, first of all?
1 + 1 is 2. 2 + 1 is 3. 2 + 2 is 5, right, basically.
Exactly. Every number in the sequence, besides the first two, really, every number in the sequence is just the addition, is just the sum of the two previous numbers. So 13 is, so 2 is 1 + 1. 3 is 1 + 2. 5 is 2 + 3. 8 is 3 + 5. Right? That's the pattern. But remember, an explicit form, right, is where you write each AK, or I'll just to let you know the letters can be anything. Let's say each CJ, no, I won't confuse you. Each AI equals f of I for all I greater than or equal to some starting index m. The point being, remember, explicit form had you write every single term as some function depending only on index, all right? So those were things where it's like you could describe every term as like the index squared plus 1 or something like that, or 2 raised to the index or something. But here, the way we describe this sequence in words is sequence of values starting with 1, 1, and continuing, and I'll say, and forming new terms by adding the two previous terms. The point is, every term here is dependent on the two previous terms. Every term after 1, 1 is dependent on the two previous terms. The point being, we can't really get an explicit formula for this because every term depends on more than just the index. We need to know more than just the index. We need to know the previous two terms to calculate it. Make sense? So this brings us to recursive form. And I'll do an example first with the Fibonacci sequence. So the recursive form of this sequence right here is, we'll say A0 = 1. A1 equals 2. And then AK, for example, is going to equal AK minus 1 plus AK minus 2 for all K greater than or equal to 2. Does that make sense? This totally defines the Fibonacci sequence as we want to define it. Oh wait, actually, I'm sorry, this would be 1 right here. 2 ones to start out. Now these right here are called our initial conditions. Because we need those to make our recursive formula work. And by the way, we call it recursive, right? You guys are CS majors, right? A lot of you. Because that's exactly what this is, like really similar to what recursion is in computer science, right? Recursion in computer science might have some method or function or that you keep plugging back into itself. Well, that's what we have here, right? Think of this as the method or function you keep plugging back into itself, where this is called the recursive formula. This is the range. The point being, this is like the recursive method or function. This is the thing you keep plugging back into itself. But you need some seed values to start with. Those are the initial conditions. So the way you'd work with this, just to get back, just like if you had this form, you have the standard form, the way you calculate it is you go, okay, well, I'll start off with A0 equals 1, and then A1 equals 1. Okay, now what do I do when the index is 2 or bigger? Oh, hey, when the index is 2 or bigger, what you do is you calculate A2 by doing A2 minus 1, so 1 less than 2 is 1. You're doing A1 plus 2 less than 2 is 0, which is 1 plus 1, which equals 2. And 3 is bigger than or equal to 2, so we use this recursive formula. That's going to be A3 minus 1, so A2, plus A3 minus 2, which is A1. A2 we just calculated to be 2. A1 we know is 1, so this is 3. And then I'll do one more. A4, right? 4 is bigger than or equal to 2, so we use this recursive formula. So we do A4 minus 1, which is A3, plus A4 minus 2, which is A2. A3 we just calculated to be 3. A2 we just calculated to be 2. This is 5. The point is we're recreating this sequence right here. So this is the recursive form. And just like the explicit form, it is an equally valid way to write this sequence. It's not necessarily just like kind of describing something that already exists. No, like this is the definition of the sequence. Just as much as this is. In fact, maybe even more, because if you just had this right here and you didn't know what the next number was, it would be confusing, but this tells you exactly what the next number is. And like I said, this can actually be done with explicit form. Any questions?
I'm all good.
Oh, Safa's back. Awesome. Cool. I heard that one, Safa. Good. Yes, this is recursive form. It's another way to write sequences, and it's important because the way to write sequences we might not have been able to write before. And so in general, the recursive form looks like this. We have some initial conditions. So I'll say, where should I start? I'll say let's have AM equals something. AM equals something all the way down to actually I don't want that. Let's have AL equals something, AL plus 1 equals something, all the way down to AM minus 1 equals something. These are all initial conditions, so they're initially defined. They're just numbers. They're not equations. They're just numbers. And then we have that AM is going to equal some function of AL plus 1, all the way out to M minus 1, and M itself for all, actually no, I want AK here. For all M, or for all K, this looks confusing. All I'm saying here is that you have some initial conditions, you have some recursive formula, and then you have the range. This recursive formula can depend on the index, just like the explicit formula, but it also can depend on, actually, well, it's hard to write out, but let's just use what we have before. The point is, we have initial conditions. And then we have AK equals something for all K greater than or equal to M. And here we have a recursive formula dependent on the index K in previous terms. Okay, so for example, let's say we have A1 equals 3, and then we have, and then we have AK equal to 3, AK minus 1 for all K greater than or equal to 2. Well, if we have this is just a definition of a sequence, and the way we can write it out in standard form is what we can do is we know that A1 equals 3. That's just given us. Now then A2, well, we don't have an initial condition, but we know, oh wait, 2 is bigger than or equal to 2, so we can use this recursive formula. And this says it's going to be, sorry, I miswrote this, 3AK minus 1 plus K. Doesn't change our initial condition. But now A2, like I said, 2 is bigger than or equal to 2, so we can use this recursive formula here, which tells us A2 is going to be 3 times the previous term, which is 3, plus the index K, which is 2. 3 times 3 is 9, plus 2 is 11. Then A3 is going to be 3 times the previous term, right? K minus 1's previous term, which is 11, plus 2, which is 33 plus 2, which is, I'm sorry. It's going to be 3, sorry. So it's going to be 3 times the previous term, 3 times 11, plus K, the index. The index here is 3. So 3 times 11 is 33, plus 3 is 36. I'm going too fast. A4, we see that AK is 3 times the previous terms. It's going to be 3 times A3, which is 36, plus the index. 3 times 36 is what? 90 plus 18, which is 108 plus 4, which is 112. It goes on like that. Any questions on how you calculate the terms of a sequence given the recursive formula? Well, then let's do another one until we have questions. Let's say we have B1 equal to -2, B2 equal to 3, B3 equal to 2, and we have BK equal to, not sponsored, BK minus 1 plus 2, BK minus 2 plus 3, BK minus 3. For all K, what should the range here be? K bigger than or equal to what?
Three.
Actually, no. Sorry about that. 4. The reason we can't use 3, Herman, is because if we use 3, that would be saying to calculate B3, we can use this formula here. And so that would mean that B3 is going to be, well, 1 less than 3 is B2, plus 2, 2 less than 3 is B1, plus 3, 3 less than 3 is B0. Then B2 we know is 3 by definition, plus 2 times B1 is -2 by definition, plus 3 times B0. Oh, there is no B0, right?
Right.
Not defined in this problem. So we don't want to use 3 here because we're into an issue. Also, we already have 3 defined. We want to use 4. But this points out a really good relationship between all these things. And that is note we need initial conditions defined for here's what I'm trying to say. It's hard, what did I write down? It's hard to write down. Here's what I'm trying to say. If we have this explicit formula, BK minus 1, 2 BK minus 2 plus 3 BK minus 3, we know it works for all K greater than or equal to 4. That means we better damn be sure that we have initial conditions for B1, B2, B3, because we're going to need them to calculate B4. So we need initial conditions defined for furthest back term B4 depends on. The only reason we use B4 here is because we said K is equal to 4. The point is, whatever the first range is, right, we need initial conditions defined for furthest back term B4 depends on and up. The point being, right, if we just do like an aside here, what if I had a different sequence and we know the recursive formula is CK equals K plus 2, CK minus 2 plus 7, CK minus 11. For all K greater than or equal to 11. How many initial conditions do we need to make this work? to really define a sequence and have no gaps or holes. You guys understand what I'm saying? Like, do we need a C2, for example? Do we need a C3, C0, C1, C10?
Yes, don't you? Or no?
Yes to all of those, right? So where does it start specifically?
It starts at 2. Or, yeah, let's say 2.
So here's the idea, right? This formula should work if this works for all k greater than or equal 11, which it says it does. That means we should be able to calculate C11 to equal the index, which is 11, plus 2, C11 minus 2, plus 7, C11 minus 11, which is 11 plus 2, C9, plus 7, C0. So C11 is dependent on C9 and C0. And so if that's like the first thing in a recursive formula, if 11 is the first one we use, well, we definitely gonna need 9 and C0 just to be initially defined. Because we use it here. Does that make sense? So we're definitely gonna need a C9 and a C0 up here. How about, do you think we need C1 for anything? First of all,
No.
since that we need C0 and C9, do you guys see why we need initial conditions there to make this work? Is that a yes? It's not rhetorical.
Not really. I don't understand why it couldn't. Like, I mean, I'm assuming at some point like it messes up the equation, but I'm not sure exactly why it would.
Thank you for stopping me, Herman. So the idea is, legitimately, let's say I gave you, this is the recursive form. Let's say I gave you C10 equals 2 and C11 equals 5. And then you go to try to calculate, I'm sorry, let's say I just gave you initial conditions C8 equals 2 and C10 equals 5. And then you go to calculate C11. Well, what would C11 be? Because remember, based on this recursive form right here, we should be able to figure out the sequence. But C11, I mean, what's that? That's for all k greater than or equal to 11. So C11 should be using this formula. C11 should be 11 plus 2, C11 minus 2, plus 7, C11 minus 11. 11 plus 2, C9, plus 7, C0. But I haven't defined a C9 or a C0 up here. So without these being previously defined, I can't calculate what C11 should be. So this recursive formula can't define a sequence for me.
Yeah, that makes sense.
Makes sense? Good. So that's why we definitely need a C2 and a C9 in the initial conditions somewhere. We definitely need a C9. Notice we didn't use C8 or C10, so maybe we don't need those. Do we need a C1, for example? I'm sorry, C0, not C2. Do we need a C1, for example?
I'm assuming you don't need anything besides those two because otherwise everything else will be defined, technically.
Well, let's think about it, right? What would happen if we try to calculate C12? Well, then C12 is going to equal, well, that's going to be 12 plus 2, C12 minus 2, which is C10, plus 7, C12 minus 11, which is 1. So in order to calculate C12, which we should be able to do, because this recursive formula should work for all k greater than or equal to 11, we would need to know C10 and C1. So we definitely need C1 and C10 previously defined. Otherwise, this recursive formula wouldn't make any sense because we wouldn't have these values we need to calculate it. Does that make sense?
Yeah, totally.
Now, here's the question. Do we need a C2?
Yes, because if it's C13, then C2.
Exactly. We need a C2 and we need a C11. That's what C13. Actually, no, we don't need C11 because that gives it to us. It turns out you're going to need a C3, C4, C5, all the way down to C10. The reason being, like we said before, if we just keep trying to calculate C13, C14, C15, C16, right? The point is we can see that this k minus 11 part, which is like the furthest back term, this goes 11 terms further back. We can see that this is always going to be less than 11 until k gets to 22. When k is 22, we get that C22 equals 22 plus 2, C, 22 minus 2 is C20, plus 7, C22 minus 11 is C11. So at this point, right, at C22, 22 and above, C22 is only dependent on terms calculated here in the recursive formula. Before 22, C11, C10, C11, C12, C13, C14, 15, 16, 17, 18, 19, 20, 21, all of those had terms dependent on something, a term before C11, dependent on C10, dependent on C9, dependent on C8, dependent on C7, 6, 5, 4, 3, 2, 1, 0. So the point is, we need all of these terms as initial conditions just to get this sequence off the ground, just to calculate the first 11. And then once we have that, then we're good to go. Then we can start plugging things back into themselves and it kind of keeps going. If that makes any sense. So the point is, that's how you should be looking at these things. If you look at this formula right here, notice the furthest back sequence is 3 further back, meaning that we're going to need 4 minus 3, 1, 2, and 3.
So for this example, if B0 was defined, could we do it from 3 then, greater than or equal to 3? If we had B0?
Yeah, exactly. If B0
Right.
was defined, then we could do it from greater than or equal to 3.
Right, gotcha.
Because then we could go that far back and see that. Does that make sense? So, yeah, so in general, when you guys are making these recursive sequences, what time is it? So I thought, when you guys are making these recursive sequences, be very sure that you have enough, that you have initial conditions defined from the furthest back dependent term in the very first term you calculate with the recursive sequence up to where the recursive sequence starts. And so like the way we think about this is that we kind of have B1, B2, B3, B4, B5, B6, on and on and on. Right here, this is where recursive formula takes over. At k greater than 4. And this side is just initial defined conditions. And the point being, to make this recursive formula work, right, you need to make sure that we have enough initial conditions to be able to plug in to the very first recursive formula here. So in order to use B4, we need to know B4 minus 3, which is B1. This is the furthest back term. You know B1. So therefore, we need initial conditions B1, B2, B3. And then the recursive formula takes over. So for example, just to really make sure we have this, let's say we had G I equals I cubed plus the sine of GI minus 1 plus the cosine of GI minus 10 for all I greater than or equal to 2. What initial conditions do we need to make this work?
We need G1, right?
We're definitely going to need G1. But in fact, let's see, we have, so our recursive formula takes over at 2. So we have G2, G3, G4, G5, on and on and on. Here's where the recursive formula takes over. Let's look at the first term in our, when the recursive formula takes over, which is G2. To calculate G2, what do we need?
G1 and G negative 8.
Yeah, G1 and G negative 8. So that tells us that we're going to need G negative 8, G negative 7, all the way up to G1. You find where the recursive form takes over, and then you ask yourself, what's the furthest back term I need? That's what you need to start with, all the way up. Does that make sense? Let's do one more. Let's say we had CJ equal to 100 raised to the CJ minus 5 plus 1000 to the CJ minus 4 for all J greater than or equal to 10. So then a recursive formula takes over at C10. So all of these can be calculated using the recursive formula. Now the question is, what's the how far back do our initial conditions need to go?
They need to go to 2.
Why 2, Safa?
At least for you plug in 10 into CJ minus 8, and then
Oh, this is a 5 right here. I'm sorry.
oh my bad. Then it would be 5.
Perfect, right? We need at least C5 and then all the way up to C9. So that's the idea. And in real life, we don't usually work backwards like this. Well, sometimes we do. But the point is, we need at least these defined for this recursive formula to make any sense. It's okay if we had a C4 and a C3. They would just kind of be there tacked on at the end. But in order to make this recursive formula make sense, we need at least to go as far back as C5 to be defined initially. Good. I'm glad we went over that. I hope that makes sense now. I hope you guys at least get it. And the point is, the reason you need that is because otherwise, if you try to do it, you would just find out, oh, I don't have the numbers I need to calculate the next term in the sequence. So real quick then, to calculate what the sequence would be in standard form, we'd have B1 is -2 as defined, B2 is 3 as defined, B3 is 2 as defined, then B4, here's where our recursive formula takes over because this works for all k greater than or equal to 4. We'd have B4 is going to equal one term less, so B4 minus 1, which is B3, plus 2 times 2 terms of 4, which is B2, plus 3 times 3 terms of 4, which is B1. And that just equals B3, we know is 2, B2 we know is 3, and B1 we know is -2. And so again, that's why it was so important that we had a B1, B2, and B3 here, because we needed to use those values to start off this recursion. And so that's going to be 2 plus 6 minus 6. So these two cancel, and we just get 2. Now B5 would be one term before, which is B4, plus 2 times 2 terms before, which is B3, plus 3 times 3 terms before, which is B2. Now B4 we just calculated to be 2. B3 we calculated to be, oh, that was defined to be 2. And then B2 was defined to be 3. This is 2 plus 4 plus 9, 6 plus 9, 15. I'll do one more. B6 is going to be one term before, which is B5 plus 2 terms before, which is B4 plus 3, B3. B5 we just found to be 15, plus 2 times B4 is 2, plus 3 times B3 is 2. 15 plus 4 plus 6 is 25. And notice now B7 is kind of like, imagine recursion is like a gas engine, right? An internal combustion engine. We have to start to crank it, but then eventually it takes over for itself. It's a cycle. Once you get to B7, that's where the engine takes over for itself, because here we get B7 by definition of the recursion is 1 less B6 plus 2, 1 less B5 plus 3 B4. But notice B4 is where the recursive formula started. So nowhere here we're using initial conditions. Now the recursion can feed itself. We just need to put these 3 initial things to feed it first, to seed it, right? So it can get started, and then it feeds itself as it goes on. And just for practice, B6 we found to be 25, B5 we found to be 15, and B4 we found to be 2. So this is going to be 25 plus 30, which is 55, plus 6, which is 62. Any question on this? My voice got very high. I'm a man. Any questions? Have you considered Allstate? Good, good. Well, I hope this makes sense, because recursive formulas are going to be nice to have them down, because we get to start induction proofs next class, but that's not this class. That's next class. So have a great day, everybody. You can relax for a little bit.
Thank you.
You're welcome. Thank you, Tur. Thank you, Safa. Thank you, Herman. Oh, wow. We went over. Sorry about that. We really got version there, but I'm glad we did. Yeah, but anyway, have a great day, everybody.
You too. Bye, Professor.
Bye, Safa.